building future innovators and creative thinkers. Security in embedded systems is getting critical with each passing day as more and more devices are getting connected to the internet. This session will cover topics such as security threats for automotive and edge devices, security hardware security capabilities, secure boot mechanism, secure world software, non-secure world software, and secure device management. By participating in this deep dive program, students can expect to learn in depth from the subject matter experts, get their questions related to the webinar topics answered by NXP subject matter experts, obtain a certificate of participation by NXP, learn how industry-academia relationship can be strengthened, as well as enable the branding and social media marketing of the university by the NXP India page. Before we move ahead with the program, I would like to give a brief overview of our prestigious institution. SRM University AP, located at Neerukonda, Mangalgiri Mandal, Guntur district of Andhra Pradesh, is a world-class university in creating and disseminating knowledge and providing students with a unique learning experience in their chosen field of scholarship that would best serve the society and betterment of mankind. It is an interdisciplinary institute combining academic rigor, excitement of discovery, creativity, and entrepreneurship, delivering world-class research-based education, creating new knowledge and innovations, as well as providing an inspiring and stimulating environment for a diverse campus community of faculty and students. While its origin goes back to the establishment of Nightingale School in 1969, now the new future begins with SRM University AP, the global institution of world-class opportunities. I would now request the head of the ECE department, Dr. Ramesh, to introduce his department.
Thank you. Good evening, all of you. Thank you, Surinder and Pankaj sir, for taking your time to share your knowledge with our students and faculty members. So I am Ramesh Vaddi, Associate Professor and HOD of the EC department. So here we have some faculty members and students from second year and third year EC students who have gathered here. And so I'm happy that you're taking the right topic because as we can see, many edge devices are increasing in the edge computing and IoT applications. So security is becoming very critical. And similarly, with increasing applications like autonomous driving vehicles, drones, and so electric vehicles coming forward, like you can see, definitely security of these systems is going to play a very significant role. And I'm happy to mention that here we have at SRM UP, EC department is hosting hardware security research group where many of our students are PhD scholars and MTech and BTech students are working on some of the lightweight authentication protocols, PUF and TRNG based hardware security methods, and DP attack resilient, how to secure the circuit. Like that, people are working both FPGA and ASIC based implementations. So we'll be very happy to connect later and we can have a more discussion with the faculty members and versus how to take things forward. So with that, I will hand over things to you. Okay, thank you.
Without further ado, I would now like to invite our two speakers, Mr. Surinder Kumar, Senior Principal Engineer, and Mr. Pankaj Gupta, Software Architect, to take over the session with their respective talks. Over to you, sir.
Yeah, hi, good evening, everyone. Before we start, I would like to request Mr. Manish. He is he's the brainchild behind this complete show, and he's organizing this session, this campus connections last many years, and helping students over the complete India. And yeah, over to you, Manish, for a few words.
Yeah, thank you, Surinder, and my dear friends, good evening to all of you, and thank you, SRM. University to giving us an opportunity to share this platform, and thank you to NXP management team. Basically, NXP India management team is very committed to support universities in all possible ways. And this is one of the way, NXP Campus Connect program, which we are running, on every first Tuesday, we are, sharing the technology and innovation related to VLSI topics. And the third Tuesday every month, we are, sharing the things with respect to the system engineering. When we are saying system engineering means it is a complete system knowledge which starts from the verification, validation of, and the different types of firmware engineering, software engineering, complete system related topics. And yes, today's topics is a very touchy topics because this is related to the latest innovation and the evolving things which is happening in the security domain. It's basically cyber security. We are going to talk about a lot of different types of cryptography which is happening, and now security is touching each and everything because terabytes of data is moving from one node to another node. So this is very important. And as you know, NXP is very strong in the automotive segment, and automotive segment is moving through a very strong transformation, which is not just in the field of EV, but also in the field of autonomous driving, connected vehicles, and a lot of stuff which is happening in this area. So yes, with this, I'm not going to invest much time, but my request, all of you to join these sessions and get benefited with all these sessions. And thank you, HOD, EC, and other respected seniors there. And thank you, ma'am, for having very nice introductions of this one. And without investing much time, I'm going to hand over this Surinder, who is our architect and having 21 plus years of industry experience. He is a well-established leader in this segment. Pankaj Gupta is also very innovative, and a lot of innovation he did in the security and cryptography. He is the key member of of this drive, which is very, very important, not just from an NXP perspective, but also from our customer perspectives. So yes, guys, I'm going to hand over this platform to you. Please make best use of this next 60 plus minutes. And for all attendees, online plus the physical presence in the hall, you can note down the queries after this session. We are going to answer all your queries, or maybe you can use our chat box, which is accessible to all of you. You can write the queries there, and later we can take all the queries before closing this session. So thank you, Surinder and Pankaj, for putting a lot of efforts in creating all this stuff, and all the best. Over to you, Surinder and Pankaj.
Thank you, Manish.
Okay, thanks. Thank you, Manish. So let me start sharing the screen. Yeah, so my screen is visible. Yeah.
Yes, make it a full screen.
Yeah. Okay.
Yeah, go ahead.
Yeah. So yeah, so as Mani said, today topic is very touchy and very important topic, that nowadays the devices with embedded systems are increasing day by day. We are having touching embedded system devices every day in our every part of life, and this leads that security becomes very important part in embedded system, because when we say security, so that no other entity can access the information in our devices, no other entity can modify the content in our devices. So today we will talk about how the security in NXP devices is established, and how security is important for the NXP. Yeah. So, yep, myself Surendra Kumar, and I am working as a senior principal engineer for automotive software. And here I am responsible for defining the architecture for the security firmware for NXP automotive devices. And this is my colleague Pankaj Gupta. He is the architect for security connected edge devices, and he will take the later part of this presentation.
Hi.
So yeah. So as ma'am said, here is the agenda for our presentation. So briefly, first we will start with the security fundamentals, so that everyone gets aware. When we talk about the hardware security compatibilities and secure boot. So first we will go through the security fundamental. Here we will we will discuss what are the various cryptographic algorithms, why they are used, I mean how they are used, right? So first we will try to cover security fundamentals, and then we will go through each of these topics in detail, like what are the various security threats for the devices, what are the various hardware secure capabilities that NXP is offering, how do we establish the secure boot in NXP devices, or we will talk about the generic flow for the secure boot, right? Then we will talk about the what is the differentiating factor between a secure world software and non-secure world software. There we will be using various terms like ARM, trust zone, and various other terminologies for the secure world software. And in the end, we will talk about the device management. So the device management is also a very important aspect when you say that this device is secure. And so management requires various capabilities. So we will discuss device management in detail at the end of the presentation. So first of all, I think everyone is aware what is security. When we say secure, so basically security is say that okay, when I say my device is secure, it means that my device is having the confidentiality. It is having the proper integrity mechanism. It is implementing the authenticity mechanism. It is available whenever it is required, right? And it has the mechanism of non-repudiation, right? So these are the basic whenever anyone says that okay, I am secure, so it will follow all these 5 principles, right? So when I say confidentiality, it means that I will keep my data secret, right? So whatever information I am having in my device, I will make sure that this data is not available to any other entity whom I am not desiring to share, right? So the confidentiality is the foremost or the most important aspect of a secure device. The second aspect is the integrity. So when we say the integrity, it means that okay, I have put data into my device. I say that okay, I will not share this data with anyone else. But what about if the data gets corrupted, or what about if the data gets changed at my device, right? So it means that I need to keep my device integrity safe so that no one else can change the content on my device. The third important aspect of a security is authenticity. When we say authenticity, it means that I will allow access to access this data only whom I am whom I know that okay, he is the authentic entity and I can share my data to this particular device. So authenticity is established whenever we do any kind of transaction with our device, right? And then these are the availability and non-repudiation. Basically, this says that okay, my device is available whenever it is required to share the information, right? Provided the receiver has established its authenticity and confidentiality. So these are the goals which need to be fulfilled by any device which says that okay, I am secure, I am establishing the security on my device, right? Now the first important, so now we will discuss each of these points in detail that, oh, okay, when I say that my device is implementing confidentiality, so how do I maintain? So in order to establish the confidentiality, there are various encryption and decryption algorithms, right? So we will go from very basic, right? So I think every one of you might have heard about, okay, this is Bob and Alice communication. So there are two entities, right, who wants to communicate with each other, right? But they want that whatever they are communicating with each other, it should not be accessible to anyone else, right? For example, there is an Eve, right, who wants to intercept that information, and he wants to read it, right? But in this case, what Bob and Alice will do, that they will establish some kind of mechanism so that this data, even when Eve accesses the data, it gets hold of the data, but it is not able to make out the from the data. So this is called cryptography, right? So what we do that when Bob sends the data, it will encrypt the data. It will encrypt the data, and when Alice will receive it, in this case, Alice is transmitting the data, and Bob is receiving the data. So what Alice will do, that whenever it transmit, it will first encrypt the data, and Bob will decrypt the data at its own end to receive the original data, right? So this is how encryption works in a typical network scenario whenever two devices are communicating with each other, right? So at the transmitting end, there is an encryption function which will encrypt the data, and at the receiver end, there is a decryption function which will decrypt the data, right? But in case of encryption, there are multiple algorithms, right? So typically we divide encryption into two ways. One is called symmetric encryption, another is called asymmetric encryption. So first we will discuss about symmetric encryption. So in case of symmetric encryption, there is a there is a shared key. I mean, there is a same key which will be used by both transmitter and the receiver. So what they will do that they will first share that key. They will establish that, okay, this is the key that we will use to encrypt and decrypt the data. So that's why it is called symmetric, that there is a common key for both encryption and decryption. So, so in this case, the transmitter will encrypt the data plain text with that key, and it will be transmitted on the network. And on the receiver side, the same key will be used to decrypt the data. Right. So this is called, and for the symmetric encryption, there are various algorithms like AES algorithms and SM4 algorithms. Right. And AES also has multiple mechanism like AES CBC, AES OIB, AES. So there are various multiple algorithms in AES as well. Yeah. So in case of symmetric algorithm, we basically meant so what target we are achieving? We are achieving the confidentiality. So in case if someone intercepts that communication, even in that case, it will not be able to make out the original data because it will not have access to the key. And these algorithms like AES and other algorithms, they are so robust that if you don't know the key, then in order to extract the original content, it may take thousands of years to extract by using the brute force method, right? So in this case, the key is shared, right, between the transmitter and the receiver, so that they can encrypt and decrypt the content, right? Now, but in this case, there is a challenge, right? How do you, for example, the transmitter and receiver are sitting very far, right? Then it becomes a challenge that how you will share the key, right? So in order to overcome this challenge, a new cryptography algorithm was established, which we call public key cryptography. So in case of public key cryptography, there is a key pair. What is the key pair? So in the key pair, there is one private key and there is one public key. So as the name suggests, the public key means that this key is available to everyone, and private key means that, okay, this is the key I will not share with me and with anyone else, and I will keep it with myself. So how does this mechanism works? So that everyone, for example, there are two entities who are communicating with each other on the network. So both the entities will generate a key pair on their device, right? And as part of key pair, one private key and one public key will be generated. Now, what each of the entity would do that it will share its public key, and it will keep its private key to itself only. So now whenever it has to transmit any data, so what it will do that it will encrypt the content with the public keys, right? And and then at the decryption end, whoever has the private key, they will basically decrypt the content. So for example, Bob has to send the data to Alice. So what it will do that it will take Alice public key, encrypt the content, and share it to him. Now, since Alice is only having its own private key, so Alice only can decrypt the content and can access its data. So this is how public-private key mechanism works in a real-world scenario. Right. So, but in case of asymmetric algorithm, so yeah, so here in this example, it is showing that, okay, it is taking the other entity public key and trying to encrypt the data, and at the receiving end, it will take its private key and decrypt the content. Yeah. So this is how the asymmetric mechanism works, right? So in this case of asymmetric mechanism, it is important to generate a pair of keys, and the pair of key is called private key and public key. So private key will be used for decryption and public key would be used for encryption. So but the asymmetric algorithms are not used just for encryption and decryption purpose, right? So they have other objectives as well. So here we can use the asymmetric algorithms to achieve our objective of signature verification. So we will discuss about it, that what is a signature, how do we verify the signature, right? So asymmetric algorithms has two objectives. One is you do the encryption, right? And another is we do the authentication, right? So we will discuss about authentication as part of later in the presentation. Yeah. But there is a disadvantage with the asymmetric mechanism, that they are slower, right? They are slower, and the keys which are used typically are larger in size. For example, there is a RSA encryption. Here we have the key size of 1K, 2K, and 4K. But then there is a ECIS, ECC based public this mechanism, signature verification mechanism. Here we have the key size as of small, but they are very inefficient. I mean, when we say inefficient, it means that they take longer for the signature verification and signature generation. So when we talk about these asymmetric algorithms, typically there are two asymmetric algorithm. One is ECC cloud-based mechanism. Another is RSA-based mechanism, right? So in RSA-based mechanism, initially the RSA-based mechanism were invented, but the key size in the RSA-based mechanism is of big size. We have 2K and 4K. ECC-based mechanism, they work on the principle of log curves, right? They have the smaller key size, but they have in terms of they are quite complex to implement, and they have better performance as compared to RSA-based mechanism. So asymmetric cryptographic algorithms, as I mentioned previously, they provide confidentiality. I mean, we basically we can use them for encryption and decryption mechanism, as well as they provide the authentication mechanism where we can establish that the sender, where we can establish the sender's identity. When we say the sender identity, it means that we can verify that the sender who is sending the data, he is authentic. He is the right person with whom we should start communicating. So these are the various, various kind of key lengths and various kind of algorithms for both symmetric and asymmetric. So in case of symmetric, we have typically which key length, which is of 128 bits, 256 and 512 bits. The algorithms in case of symmetric is typically AES, but in case of asymmetric, we have RSA and ECC. When we talk about performance, symmetric cryptographic algorithms are fast in nature, right? But in case of asymmetric cryptographic, they are a bit slower as compared to symmetric cryptography. Typical applications for symmetric algorithms is that when you have to do the encryption of bulk content, then we do use symmetric cryptography. But when we have the small, where we have the signature verifications and we have a small where we have to encrypt the keys, right? Then we use asymmetric cryptography. So this is important point, that encryption of key, right? So for example, if you have to do the symmetric cryptography, so in order for symmetric cryptography, we need to have the common key. So we can share the keys using the asymmetric cryptographic algorithms. So once we share the key, and then both of the entities can have that key, and then they can use that key for particular symmetric cryptographic algorithms. Now, this is how we did the confidentiality, how we maintained the confidentiality, right, using the symmetric and asymmetric cryptographic algorithm. The next important concept in security is how to establish the authenticity. So when we say how to establish authenticity, means that we need to ensure that the person with whom we are communicating is the right person. So how do we establish? For example, even when we go to in the real world example, right? When we go to any, when we enter even to our office premises, or when we enter into our school college building, right? We show our ID card and we say that okay, we are the right person to enter into this building. So this is how, in case of communicating on the network, we need to establish our identity, that okay, I am the right person, and you can start communicating with me. Right. So this is why the authenticity comes into the picture, so that you don't share your keys with the wrong person. Right. So how do we establish the authenticity? So basically, what we do that in case of authenticity, what we do that the person who is starting the communication, he will include the signatures as well as part of his message. So what it will do that, as part of first message, he will include the signature also along with that message, or he can do the what he can include the message authentication tag as well along with the message. So the first message is not just the only the message payload. It will have your signature or authentication tag as well along with the message. So what the receiver entity will do, that what it will take, it will use the it will use the private key of that particular, it will use the public key of that device. It will generate again the tag at its own end, and then it will verify the tag in the message. So once the tag is verified, then it will understand that okay, the tag is same what is there in the first communication message and the tag which I am calculating. So once it establishes that the authentication tag, then it can say, it can ensure that okay, I am communicating with the right person and I can start the next state of message. So this is how the authentication work, and authentication is important in case of security, that we need first step is to establish the authentication while doing the communication. So there are various message authentication functions, like there are CMAC, there are HMAC. So there are various message authentication functions, and they have various kind of algorithms as well, right? So similarly, along with the message authentication code, there are various digital signatures as well. So what we even in real world also, when we have kind of our certificates, right? So when we get the certificate from our university, right? So it is a signature from the vice chancellor, which says that okay, I am establishing the credential of this particular paper, and I am saying that okay, this piece of paper is authentic. So this is called so in case of digital world, these are called digital signature. And each entity, they so whatever, whenever they are sending the message, they will do the signature on that particular message, and the receiving entity can verify the signature. Okay, this is the these signature are correct, and I can start communicating with that particular person. So signatures and the message authentication code are the two methods by which we can establish the authenticity of our entity in the network, and we can we can do the authentic communication into the network. So yeah. So in case of there is a non-repudiation, means basically, so this is related what we discussed, that when we start communicating, we establish the authenticity of the message. But once we once we determine that the person with we are starting to communicate is not the authentic, then we will not communicate with that person, and we will disconnect that particular communication. So this is called repudiation. So here is the comparison between various authentication mechanism, right? So there are in case of authentication also, we have symmetric as well as non-symmetric. So in case of symmetric authentication, we can have our CMAC, we can have our hashMAC. In case of asymmetric authentication, we have ECC based signatures, we have RSA based signature. Right. So same here, the performance for the symmetric authentication is fast, and the performance for asymmetric authentication would be slow. In the typical application for the symmetric authentication, when we have bulk of data, need to have high throughput, then we will use the symmetric authentication. But in case of where we have small content and we have some kind of digital certificate kind of applications, there we will use asymmetric authentication. So in case of symmetric authentication, we will use symmetric keys, which we discussed previously. But in case of asymmetric authentication, we will use the public-private key pairs. So we discussed confidentiality. We discussed how to establish the authentication before we start any communication with any entity into the network. Now the next important point is how do we establish the trust, right? So basically, the trust means that okay, when I am when I am communicating with that particular device, I ensure that okay, this is the entity. There is no this entity has not been hacked. This is the if this entity is communicating with me, then it is it is communicating in a proper manner. So this is we establish. So the root of trust is very important when we discuss about the secure devices. So every secure device will establish a root of trust in itself, and that root of trust device will ensure that every software which is running on that particular device is secure. there is no authentic software which is running onto that particular device. So typically on an SoC, we have one secure IP, which establishes the root of trust into the complete system. And this IP is responsible for booting all the application cores, all the other devices into the system in a secure way. So this is how we establish the root of trust. So root of trust is so it's not that the root of trust is established from at any point. Root of trust is determined even when we manufacture the first sample and when the samples are delivered to the fabs, right? So from there, starting from there, we establish the root of trust till it is delivered to the customer. So as trust is established at every stage into the silicon life cycle. So this is why root of trust of any device is very important from the security perspective. So another important point in this security is about the certificate, right? So as I discussed previously, that in a physical world, I think every one of us has received the certificate from our schools, from universities, right? And we have the signatures which establish that okay, this piece of paper is the authentic, right? So similarly, in the digital world, we have the digital certificate, and we have a root certificate authority which issues the certificate, and that root certificate. Root C authority is the authentic. That is established that okay, this is the device, this is the root authority which can issues the certificate, and those certificate can be used further to issue another certificate. So there is a chain of certificates in the digital world, right? Because the network is very big, there are so many nodes which are communicating with each other. So not each of those node can have its can have the root certificate. So what do they do? So they have a chain of certificate, but the root of the certificate is the root of trust device. So that root of trust establishes the first certificate, and then there is a chain of certificate which further issues the next level of certificate. So certificates are also important. So whenever we communicate, we start communicating into the network, then first entity which communicate, it shows the certificate and it says that, okay, I am the right person to start communication. So for example, here it shows the chain of certificate, right? So CA1 is the root of trust. It will issue the first certificate, then it will CA2 will use the CA1 certificate, then it will issue further certificate on its behalf. So similarly, CA3 will use CA2 certificate and it will issue the certificate on its own behalf. So this is how certificate chaining works, and we establish the authenticity into the digital network. So now I will invite my colleague Pankaj. He will take the session from here. He will discuss more about the physical devices. So typically more about the NXP devices, that what are typical threats and how do we manage those threats, and how do we establish security in our NXP devices. So over to you, Pankaj. Yeah.
Thanks, Surinder. My voice is audible, yeah?
Yeah.
Yeah. Thanks, Surinder, for sharing the details on cryptography root of trust. Myself, Pankaj, has 20 plus of years experience and authored uh, some chapters on security and cryptography in books. So I'm a community maintainer for TFA and TFA Trusted Firmware Architect for Cortex-A for NXP SoCs. And I'm also the maintainer for NXP hardware IP CAM in Linux community. We talked about the basics of cryptography, root of trust, asymmetric cryptography, symmetric cryptography. These all can be implemented using software implementations, but software implementations are not trustworthy. So as you know, these edge IoT devices are deployed in any environment where hacker has physical access and unlimited time to hack into the device. So hardware-backed cryptography or embedded security is a key to such attacks. So I'm going to talk about type of attacks on the embedded surface. Uh, Screen, I think. Are you seeing the slides?
No, Pankaj. Yeah.
Okay, just now. Oh, let me share again.
No, Pankaj.
Pankaj, any issues?
I'm trying just a moment.
You are visible on the screen.
Yeah. Let me share my desktop whole. It's better.
Wasim, can you support?
And now I think we can see the desktop, Pankaj.
Can you see this slides?
No,
Not
the
yet.
slides. Yeah, the slides not there. So you need to share the another screen, maybe Pankaj.
Okay.
Stop sharing and then share again and with another screen.
Share the screen where the presentation is. I think you have multiple screens.
No, single screen. Let me share again.
Then you have to,
Yeah,
Can you see now?
Yes, make it a full screen. Yeah.
Yeah. So these are the typical. So this is the SoC. We're trying to show you here, which has CPU, a core, then boot ROM, then peripherals.
Pankaj, I think the text is also coming in the bottom, so you can select the mode, different mode.
Okay.
No, below. Yeah. Perfect.
That's fine. Yeah. Okay. So yeah. So this is the on the left side you can see this is a SoC, a typical SoC which has a CPU, which is actually executing the instructions, and the boot ROM, the peripherals, the like LAN, PAN, and WAN. Then we have a system controllers which controls the clocks, resets powers, and there is an internal SRAM, secure RAM or on-chip. So uh, these are the typical components of a SoC, in which each component can be attacked using a cache. By attacking the cache, like ARM V8 has two types of worlds, secure world and non-secure world, where you can have two types of caches. So secure world cache is different from the normal world's cache, and we'll talk about in detail in coming slides about the worlds, but you can try to access the cache from normal world to the secure world. So this kind of an attack is possible. Earlier, now there is some guarding being added by the ARM and the Intel. Then we have bypass secure boot checks, like when there is a secure boot as in continuation to the root of trust, wherein when the root in establishing the root of trust, we compare the certificates to the stored certificates within the SoC, and if these checks can be bypassed, then this root of trust can be broken, and a user can use this device for illegal purpose or unintended purpose. Then we have a peripheral like WAN, wherein we can have when we are communicating from this device to the edge or IoT or the backend server. These can be eavesdropped, like trying to hack into the encrypted data being sent over these interfaces, and try to reverse the cryptography and get the plain text. Then we have external code and data accesses, where we have DRAM, which is DRAM is outside the SOC. So we can try to read. Again, there is a two types of worlds come in place, which are working on DDR, executing from DDR, and those are partitioned using various hardware IPs. One of them is TZASC, Trusted Address Space Controller, which is an ARM IP. So that IP, again, you can steal the data from one world to another world using memory overflow, and these are such attacks you can exploit. Then there is a clock and runtime integrity check which is going on, so you can skip. There is a glitch attacks where you can glitch the instruction, or you can skip a clock to which can skip the instruction where you might be comparing the signature, or maybe where you are comparing the key or the fuse. You're trying to read the monotony counter from a fuse. So this is another set of attack which you can put in. Then there is a cold boot and data remnants attack, where you can from the SRAM you can there is a time of attack, like when you are reading the key from the SRAM, and when you are like once you validate those keys, and then again when you try to use that image, the validated image from the SRAM, but the image is already changed after the validation. So then it is called time of use and time of verification to time of use attack. So there are very variety of attacks which is possible on an SoC. And since I started with the fact that the edge devices, the IoT devices are placed in a hostile environment where a hacker has unlimited time to hack into the device, and there's a quite a good number of attack surfaces he has. So let's talk about the security concerns of an IoT device. So as I said, it's a large attack surface. There is a commercial theft, like you can devices worth very expensive can be used for unintended use. Then there is a sensitive information across multiple devices. Then there is a cost sensitivity product, like the trustworthiness of the device, because for instance you are doing a bank transaction and using your phone or your Wi-Fi router, and that get compromised, then the banking transaction get hacked in and your secrets get logged. So that is one example here. Then the home premises, like somebody is monitoring your usage or the electricity consumption of your house, and the day when the electric consumption is very low, you can know there is nobody inside the house, and you can get inside the house. So there are the various use cases, or various like you never know how the hacker is framing his mind and like planning his attack. So you need to be prepared, and we are going to talk about in coming slides how this can be taken care and minimize this attack surface. So as I said, like this cryptography or root of trust and those things can be enabled using software, but software being run from DRAM, as I said, it is prone to attacks. So it is very crucial to have hardware backed cryptography, or hardware backed security enablement. So NXP offers multiple IPs, and these IPs are the keys offering for our SoCs, where we are complying to the different standards, security standards, and certifying our devices to be secure from various types of attack. So let me talk about. So let me talk about some of these capabilities. There's a secure boot, a secure world, non-secure world partitioning. Then there is a secure boot, which is establishing a chain of trust. Then we are having the secure storage, wherein the storage of the normal world and the secure world is totally segregated, and it cannot be read by the normal world. Then there is a manufacturing protection, so there is no cloning of the devices. Like if we have developed a SOC and we asked some company or some companies to fabricate those, so we asked them to fabricate 10, but it may fabricate 100, so 90s are cloned, so which are outside what we have asked. So that can be also protected using manufacturing protection. Then there is a key protection. Then we have tamper detect, like as soon as the device which is placed in the hostile environment get opened without authorized personnel, then the temper detection can be raised, and the keys or the secrets will be cleaned from the device. And there is a secure debug when there is an issue, because the devices needs to be debugged when they are deployed in the environment. So for securely debugging, and for securely debugging, we need to establish the secure credential before the device open up to share its logs. So this is another feature being offered by hardware security capable devices. So blocking physical attacks with temper detections. So let's start with that. Detecting temper. What is that? There is a pin. There is a pin to the SoC where there is a interrupt being. There is a jumper pins being set, and it is tied to device case. And as soon as the case is opened, that pin got short, and that got triggered, and the trigger reaches to the software, and that software, when the software realizes there is a tamper detection happen, then we clean our secret, and we move to the reset mode. So this is one way. As soon as the hacker tries to open a physical access, this type of attack can prevent the unauthorized access. Transition zeroizing the on-chip SRAM, DDR, master secrets. That's what I'm talking about. Zeroize and clean it. Everything. Those secrets. If we don't zeroize, those secrets can be read after opening the device, and that can be used in the next cycles, power cycles. Moving to the another offering for mandatory for secure boot. It's a chain of trust. So secure boot ensures only the signed images can run on the SoC. As I mentioned, devices are expensive, or devices are processing cost sensitive information, so that needs to run only the signed or the authenticated images. Otherwise, those secrets can be stolen. So this signed images can only be run, and these are the signed images being delivered from the authentic source. Like if NXP is giving SoC, then the software has to come from NXP, or for some other vendor has to give that. No other vendor software should be allowed to run. So this ensures secure boot ensures the only signed images from this right vendor should allow to be run. Then boot secure also it established a known state, a good known state to open secrets. So there are secrets which are kept at rest, like keys which are encrypted and saved as a blob on a non-volatile memory, and those blobs can only be can only be unblobbed or decapsulated based on the security state of the device. So if the secure boot is successful, then only that state will remain intact, and when the blob is deblobified, that state is being checked. If it is secure state, then only those blobs get correctly deblobified, else the key is of no use. Then there is a secure boot protection against platform repurposing, means unauthorized unintended user. Secure boot protects against that also, and unauthorized software from running. It also prevent key revocation. There is another feature which can be used, like for instance, one of hacker is able to get hold of the key. You can easily key revoke. There are you can revoke that particular set of key, so that any software signed with that particular key will not be used, and there will be only the next, and that key will be marked as blacklisted in our hardware. And when user try to use that image with that signed, that is this key revocation feature helps prevent attacker from using the older versions. Moving to what is the value of secure boot? Like what is happening when you when booting, you want this, like on-chip ROM, the ROM runs, and then it runs and the first bootloader then bootloader runs the kernel. That's what a user wants. But what you get this is that when a hacked device is running a hacked bootloader, you don't know the kernel which you are using is authentic or genuine, and this hacked bootloader can run a hacked kernel, wherein which is eavesdropping your secrets to the socket, which you don't know, and it's storing your secret somewhere, and later it can use to access your cost sensitive or critical information later. And or this is another kind of attack, like hacked bootloader, and then the bootloader is not hacked if the kernel get hacked. So this is how the cases when the secure boot is not there. So what happened if the secure boot is there? So how the secure boot, like I'm going to in detail how this secure boot images are sent, that these are the right image. So what will this is there's an image which is a plain image. Then this is a tool. This is a tool which signs the image and with the key provided. So this is a tool which takes input from the key and take the hash of the image. It calculates the hash of the image and encrypt that hash with the this key and create the signed image. So what happens, a typical case, like what happens when this board runs on, the on-chip ROM verifies this, has this input like signed image. So what it do, it signed image verifies the, first it verifies the key. This signed image also has a key, and these key is verified in the from the fuses, whether because these are the hardware fuses part of the SoC. So on-chip RAM validates this key, which is being offered by the signed image, and this key is being burnt into the hardware fuses of the SoC. This once on-chip ROM validates the key is matching to the fused key, then this key is used to uh, uh, validate this signed image to get the plain image and to execute the next level. So on-chip RAM goes to the hardware and then verifies the bootloader. This is the bootloader image which validates. And once this validation is done for the bootloader, it moves to the next level. Again, the bootloader has the access to the hardware fuses now. What happens when the kernel image, that's a signed for kernel image, is given to this bootloader to validate, it again validates the key from the fuses, and if the key is valid, then it uses this key to verify the kernel image and load this kernel image to the Linux prompt. So let's have this simplified flow of a secure boot here. So in this previous slide, if you see this hardware security fuses and on-chip ROM, everything is happened. Where this verification is a cryptographic operation. The verification and this code signing tool is a cryptographic operation. So every such operations are being done in a security engine, which is a separate IP in itself within the SOC. So what happens when the secure boot comes, the boot ROM check whether it is a secure boot. If secure boot is yes, then we validate the firmware. If it is no, why no? No is a situation when we are doing our development in the labs. So because we don't want to use the secure boot, we want to just go and skip this step. So this is very rarely it's not a case of deployment. So just to give you an idea that when the secure boot is enabled, we check the firmware signature, and if the signature is validate, then only we release the application processor to run the customer software. Else it won't release, and it will go to the reset state. and this will continue until unless the this firmware signature is okay. Now the secure boot is done. So what's now? Secure boot validates the very small piece of firmware, like bootloader. As you see, secure boot validates the firmware, then it validates application firmware, and based on this model, this is called chain of verification. This, as you can see, there is a chain of verification. There's a secure boot is validating the bootloader, the first bootloader, then first bootloader is validating the application firmware. So it's a kind of a chain getting established. So I'll talk about this chain in the next slides. And you can see the trust is starting from the security engine, the hardware inside the boot ROM. So this is part of there's another boot ROM which is part of the inside the SOC, is read-only code, which is once freeze is freeze. So we are getting away from that boot ROM code towards more of the user code, which is not residing on the SOC. We are adding, we are developing this SOC, and we are updating and upgrading the software. So this trust is moving away from the SOC. Now the chain is getting established. So boot chain. So let's talk about in more detail. Secure boot is bringing the trusted state. So what we are doing, the secure boot happening, the once the verification is successful, then the secure boot start executing the bootloader. Then bootloader verifies the firmware and give the control. This is the control to execute the firmware. Then then the signature. There are different level of firmwares. So this is the chain getting validated at each step. So let's me talk about the secure world software with this example. Because this example is well suited for NXP SOCs. So in terms of, because NXP SOCs are majorly based on ARM Cortex-A. So this is called trusted firmware for Cortex-A SoCs. The Cortex-A SoCs have two types of worlds. So responsible this trusted firmware for Cortex-A is the first stage, and like after bootloader, this is the firmware, and this firmware is responsible for partitioning of the resources. The resources, what I mean is the DRAM. Before this TFA, before this software, the DRAM is completely DRAM is available. There is no partition. But since this DRAM is going to used by Linux as well as the secure softwares, so we first partition this DRAM into using different ARM IPs. One of the IPs touch zone address space controller, that is TZ and TZC 380 TZC 400, and then we are talking about configure security state monitor. So we are also configuring the security state monitor to keep monitoring the state of the device, the security state of the device. As soon as the security state violates and switch to non-secure world, like any of the image signature is not validated or not trustworthy, we before resetting, we clear the DRAMs, we zeroize the keys and go to the fail-safe state. It also this piece of software is also enable and supports the trusted execution environment. There's the Cortex-A has two worlds, so normal world and secure world. So it also supports the trust execution environment running on the secure side of the Cortex-A. And then it also provides the SMC interface, secure monitor calls. These are secure monitor calls interface, wherein Linux kernel or the secure world OS both can interact and take advantage of the software, which has the most sensitive information, access to most sensitive information, and based on the worlds, it gives access to those information. Actually, this is the foundation to the trusted. This is the foundation of the trusted compute base, actually. So let us talk in more detail in terms of TFA, trusted firmware for Cortex-A. So if you see, this is the boot ROM, which is the first piece of software which is burnt in the SoC. It is non-modifiable. It gives the control to it first validate the signature of BL2. This is the platform initialization code. This is a very thin, non-resident non-resident bootload, primary bootloader, I would say. Once this authentication is successful, then our post authentication, the execution from the boot ROM is passed to BL2. This is the primary bootloader. This primary bootloader once then is responsible for next level of booting process. So as you can see, the boot ROM is part of SOC, but now we are going away from SOC because the trust is established. The trust is transferred from boot ROM to BL2. Now, from as part of BL2, what we are doing is we are again validating the BL31. This is the secure runtime firmware. This is a resident software, which is always residing in the as part of the ARM Cortex A, and this uh, then this validates, this BL2 validates the BL32. This is the secure OPT. This is the secure world OS. So if you can see, this is the black line. This is partitioning the world. So whatever software running here are secure, and the software which are running on the left side is non-secure. So what is happening is that BL2 is validating these images and pass the control of next level execution to BL31. This is the resident software. What it is doing, it initialize itself, do the configuration like PACI, JIC, hardware RNG, platform, runtime, image validation, key generations, whatever required to validate and to support the next level booting. So these are the features. And similarly, BL2, I missed to tell about BL2 also. The BL2 is doing DDR initialization. It is loading the it's loading the boot devices. Boot devices, by means the SD or QSPI or the non-volatile storages from where the images has to be fetched. Then the image validation, the secure boot initialization, and the TZAC, as I mentioned, it's a controller which partition the DDR. Then the interconnect of the SOC. So what we are saying, the trust is being transferred from here to here, and from here we are loading the BL32 and returning the trust anchor here. Then this is the trusted establishment of secure OS. Secure OS, this is the secure world OS, and this this passes the control now to the normal world. What normal world is doing, normal world is validating the normal world images now post validation. The blue line is telling you the validation. The BL2 validates the U-boot also. So post validation, the image is being located here. Now BL2, this BL31 passes the control to this U-boot or UFI, and then U-boot validates. Now the trust is being passed till here, and this trust is validating this kernel image, and over the validation is successful, the U-boot passes the control to the kernel entry point, and kernel is now loading. And when the Linux prompt is reached, then we can say the secure boot is established. So you can see none of the non-authentic software is allowed to run. So this is the state, and at this state, when we are running the reach to this state, the secure monitor state, the system state is secure. So this state is always being checked before working on any of the secret operations or the security related operations. Look, this is again the secure world and the normal world, where through FFA we are giving the different operations, the crypto services. There are certain crypto services you want to run through secure world only. So these normal world can use these interfaces to interact with the crypto services or the storage services managed by the secure world OS. Then let's take a use case for secure firmware update. Take an update of NXP does not offer firmware updates services. Actually, it helps or provide or enable tools to help to achieve it. For example, HSC. It verify to be flash, like it verify the firmware and for the authenticity. It provide the bootloader updating procedure by secure boot. It provides the encryption and decryption. So in our case, because encryption is done off the SOC, so the right word is to say is decryption as part of the as part of the secure boot or the secure firmware element, and controlling the system behavior, like the security monitor state is being captured and maintained throughout the life cycle of the device, and it always get compared against before doing any security related operation. So let's take an example flow. System starts with the secure boot. After verification, the secure boot verification, the firmware is the present firmware is. So we're talking about the current firmware is running, and the new firmware comes in. So what happens is the secure boot bootloader validates and validates the new firmware. So what happens? The present firmware is there, but it validates the new firmware because that is being available as part of the over-the-air update, or yeah, typically over-the-air update, or you can say there's an edge device which is having multiple IoT device connecting. So edge is also giving you the new firmware to update the IoT firmware. So there are many ways you can reach the firmware to the target device, and when this firmware is reached there, the firmware is executed. The new firmware is downloaded from the verification service, and after successful verification of this new firmware, the flashing of this firmware, or you can say replacing of this firmware happens. Because this firmware is now established its credibility. Credibility means authenticity, and the signatures are validated. Now we can update this firmware as a default firmware. So this is an integrated hardware security engine. This hardware security engine is part of secure environment inside SOC. This is an IP inside SOC, and which has its own fuses, access to the fuses, security services like hardware engines like AES engines, or AES encryption engines, or public key encryptions engines, and fuses. And so what it has a dedicated uh, uh, processors which can also used to, because these are more trusted. This line is itself is protected to side channel. There is, when this IP was designed, so these IPs are designed to be more hardened, so that they can be protected against the glitch attacks and various type of attack which we talked earlier. So application core is not used. It has its own dedicated processor, wherein these cryptographic operations are performed. For instance, verification of the image, calculation of hash, and decryption of image. So these are being done in this by the security engine, and this being requested by user applications as well as part of the secure boot. Moving on to secure element, it's another dedicated IC which is having it can control. It cannot control another IC, but it can generally improve the attack surface by having a resistance, and just extending to very specific security services. So it's a very it does not offer a wide variety of security services, only very specific to the desired scenario to scenario. These services as secure element services are exposed from this. This is another type of secure element device IC. So now talking about the non-secure world. We have talked about secure world, but lot about secure world. But how this secure world, because being used by non-secure world, because non-secure world is the reality. So we are sitting in the non-secure world, but we and from the non-secure world, when we have to do some kind of security sensitive operations, then we come to the secure world for getting things done. So part of the secure boot flow, you have seen that the normal world OS came up after validating and establishing a chain of trust, and manufacturing protection and bootloader cannot convert, can convert now, since the security state is intact as secure. So any user blob or the key blob present on the Linux kernel or non-secure world, which is of no use, which cannot be deblobified or which cannot be come into plane otherwise. When that blob is being fetched to given to the secure world to use, to convert it, so for using it has to convert to the plain text key, and plain text key then perform the cryptographic operations. But that conversion will not happen if the security state is not secure. So that is something secure world, normal world operations are guarding. The normal world operations are now guarded against the attacks by having the genuine Linux or genuine OS running, on the device. So you can say this is the user encrypted received bootloader, and key decrypted public key, and decrypted converted to the encrypted key blob. So that is a blob now. So what happened? The encrypted blob passed to OS, this OS, and this OS decrypts the app using the secure hardware. This is the hardware I am talking about. This decrypts means it decrypts the blob and loads the blob in the hardware. So what is happening if there is this security state is not met, this hardware will not load it, and it will return an error. And so this is how this ensures that whatever operations being performed using this blob on a authentic Linux kernel or authentic OS will perform correctly, else the operations won't be guaranteed. Now for let's talk about normal world security enablements which are required to further lower the attack surface. See, we are lowering the attack surfaces. Now, even on the Linux world, which is a normal world, we can further reduce the attack surface by uh, uh, application layer end-to-end encryption. So what we are doing is whenever application layer is sending any packet, like say for instance, OpenSSL is using sending any message on the network for say between Alice and Bob, so that network that can be used, that can be encrypted by OpenSSL, and this OpenSSL, so this pipe is encrypted, and when this pipe leaves the sock, the message is encrypted, and it will be decrypted only on the target device. So while doing this encryption and decryption as part of this pipe, these are the various elements get involved. There is a layer below OpenSSL. There is a CryptoDef, AFLG, the PKCS11 public key cryptography algorithm library will be used. Then there is a secure middleware framework. There's a enclave libraries, CAM libraries, trusted execution environment library. Means this can be done by a secure world. This can be done by hardware IP. This can be again is another hardware IP, secure element IP, which is actually doing this encryption and decryption. So this is protecting this protecting the sensitive data within Linux. This layer itself is protecting the data from other management layer from accessing each other. So for instance, again, the Linux security subsystem as part of application layer ensuring the system security, like dmcrypt. There's a management layer, there's a Linux layer which has dmcrypt, which encrypt the whole storage device. You can say encrypt the hard disk. I think I need to rush. Base hardware support leveraged by app layer and security system security layer. So this is the trust zone driver. Then there's an enclave driver, which is talking enclave library. This is a SNVS driver, which is maintaining the security states. The VIF job rings, which is talking to CAM. So these are the Linux ecosystem, which is helping us to reduce the attack surface again, and doing the cryptographic operation more securely. So it's in the device management. This is very important since device lifecycle is nothing but provisioning from like when the device is physically manufactured, configured, and used in the target environment. Then it is while using in the targeted environment, there are the different updates coming in, security updates or the feature updates are coming in. Then we are removing that device, the decommissioning, or you can say end of life of the device. So these are the different phases of edge device life. So this edge device evolved from firmware on like into firmware and software with the functionality tied to service capability hosted in cloud. So it is heavily tied to the cloud services because in this world of in this connected world, we have billions and billions of devices connected and maintained through cloud servers. And for that, we need to manage the cloud service to manage the device ID, each device ID and the user ID on that device, and the user ID and the service which this user is actually executing using this device. So this tuple is a key to identify whether this service is being allowed or not. So this tuple is must for this lifecycle management as a base. And this OEM and service providers needs to comply with the legal requirements, EU's GDPR and CPRA. So edge lifecycle is a must. Now edge device lifecycle is getting must and must, because even if a CCTV camera can be hacked and to not see anything which while a crime or while a theft is going on. So those kind of that requires maintenance even and decommissioning, proper decommissioning, so that post decommissioning this device can be removed or not used for unintended uses. So let me talk about this from dies to decommissioning. This is a typical diagram which tells you when the SOC is created, and until the this SOC got decommissioned. So quickly talk about while manufacturing or well the device is getting fabricated, the trust provisioning start into it. It's like the devices nowadays is not end, it is not the afterthought, we have to do a before thought. So at the time of manufacturing only, we have to think about trust provisioning, where we are anchoring the keys, the certificates inside the SOC. We burn it so that and the device IDs, we burn it inside, so that the cloning can be somehow like I cannot get into more details, but yeah, the cloning can be prevented. Then there is a server. There is an edge lock to go server. This is an NXP maintained server where when there is a third party which is using our SOC to create a device, IoT device, this device when come in play, it will establish the connection with this server to mark it as claimed, means it is there, it is available, and so it prevents here, it prevents device cloning. Say for instance, we ask this party to make 100 devices, but he made 200, so the rest 100 will not, because we know the count here. We know the count here, it is 100 only. So and this is unique. So preventing the device cloning. Now this is the, say for instance, coming in to the OEM who is managing this device. So this is a OEM management server, which again keep talking to our edge lock server, where in this device check for the onboarding. Once this get provision, it talks to this server for this authenticity, and when the authenticity is established, then only it this get operational. Then again after the onboarding, then we have to do some configuration. The configurations only allowed post this device management is successful, because you cannot rotate the camera view anywhere. You have to this is configured to particular angle, it has to remain there. Then there is a device in use. When you're using this device, there is a you have to keep sending the reports of the device being the reports being collected by the device, so you over the network. So it uses the certificates to have the genuine and authentic communication. It use we need to do the platform updates also, and other services plus and minus. So all requires the authentication and before actually executing. And at the end, when there is a decommissioning phase, like we want to get rid of this device, this decommissioning needs to be marked, so that this device is marked decommissioned here and then here, so that when this device, nobody else can try to use it. If somebody else try to use it unintended, it won't be able to access any of his services, because when it tries to talk to edgelock to go, it will be marked decommissioned. So this is how typical life cycle of a device is managed. Okay, moving to firmware attacks, updates with rollbacks. So since we talk about the firmware updates, this firmware updates, like or any type of updates are coming. So what we need to ensure that, for instance, your key is compromised. The last image was signed with a key, and that key got compromised. Now you want to use the same firmware but with different key. So what you do, you send that firmware with the new firmware update, and that firmware update will be with signed with a new key. So old firmwares won't be used. But at the same time, if the version of that firmware has to be updated, there's another case where there is a vulnerability in the old firmware version, and the new firmware version fixes that vulnerability. Then you don't want the old firmware to continue. So that there is a phonotonic counter. There is a fuse which is dedicated to a counter part of the hardware, and version is saved there. The last running firmware version is saved there. So what happens when the new firmware come in and verified and authenticated, that version number is being updated in that fuse also. So now any older version will not be allowed to run. So that is called rollback protection, and this will prevent the older compromised firmware version not allowed to be executed. So this is how image validation, that's what I already talked about. Higher level and software is involved. So for image transfer, in plus or operation validations, everything is root of trust, rollback protection, everything is tied to the security element. So where we are comparing the fuses and doing the trusted and validation of key image in a secure world. Okay, so secure boot location, the firmware, the new firmware, and so that's what is happening. That this is the old firmware, primary boot location. This is a new firmware came in. It's validated and authenticated. The system is running from here, and system reset. So once this authentication is done and validation, this firmware is this system resets and it swapped this location. So what happens? It moves here. This is swapped. If you see, this is swapped, and now system is booting from the next firmware, the new firmware, and the new image is operational now, and the firmware the firmware version, this N+1, the version is fused to the fuses inside managed inside the secure elements, which cannot be accessed, which cannot be modified without this process being followed. So now if the firmware N is again being presented, which is compromised, this fuse comparison will fail. And this comparison, if this comparison is failing, this firmware will not be allowed to run. This is what I'm trying to depict here. So conclusion here is that edge devices are vulnerable to multiple security threats, and hardware backing is the key. Software cannot be trusted. Hardware backing is a must to protect these devices to the numerous and unknown, uncountable type of attacks. Then the secure boot is one such one such process where we are ensuring the authenticate images are running, and then partitioning the secure world and the non-secure world, making that attack surface little less, because now the secure world is removed from the normal world. So now the attack surface is reduced now, and again normal world is using the secure world capabilities and various other security implementations implemented at say normal world to reduce further attack, further reduce the attack surface. So and to end of it, the device management is critical for safely provisioning and monitoring the edge devices, and finally decommissioning the device. So that's what I want to convey you guys on this security in the devices. Thank you.